In this lesson, we will build an intuitive understanding of limits and continuity. We will define limits, look at one clean example, and then connect limits to the idea of continuity at a point. First, what is a limit? The limit of f of x as x approaches a equals L means that as x gets close to a, the output f of x gets close to L. Importantly, f of a does not need to equal the limit. We also use one-sided limits. The left-hand limit uses a minus sign, and the right-hand limit uses a plus sign. The two-sided limit exists only when both one-sided limits agree. Now a clean example. Consider the limit as x approaches 2 of the fraction x squared minus 4 over x minus 2. Factor the numerator as x minus 2 times x plus 2. For x not equal to 2, this simplifies to x plus 2. So the function acts like x plus 2 near x equals 2, but there is a hole at x equals 2. Therefore, the limit equals 4. Continuity links directly to limits. A function f is continuous at x equals a if and only if three things hold. 1. F of a is defined. 2. The limit of f of x as x approaches o exists. 3. That limit equals f of a. Common ways continuity fails include removable discontinuity, also called a hole, a jump discontinuity, where left and right limits differ, and an infinite discontinuity, where values blow up without bound. Let us revisit our earlier example and define the function. So the hole is filled. Define f of x to be the fraction x squared minus 4 over x minus 2 when x is not 2, and define f of 2 to be 4. 1. Is f of 2 defined? Yes, it equals 4. 2. Does the limit as x approaches 2 exist? Yes, we found it equals 4. 3. Does that limit equal f of 2? Yes. Therefore, f is continuous at x equals 2. To summarize, limits describe what a function approaches near a point. Continuity at a point means the function has no break. The value, the limit, and the approach all line up. These tools let us handle tricky points and set the stage for derivatives and integrals.
L'Hospital's rule application. Evaluate the limit. The limit as x approaches 0 of left parenthesis sign, x minus x right parenthesis, over x cubed. We'll solve it twice. First by repeated L'Hospital's rule, then by a Taylor series visual cue. First, check the form. At x equals 0, sinus 0 minus 0 equals 0, and 0 cubed equals 0. So we have 0 over 0, an indeterminate form. We may use L'Hospital's rule. Method 1. Repeated L'Hospital's rule. Start with the original fraction. Differentiate top and bottom once. It's still 0 over 0. Differentiate again. Still 0 over 0. Differentiate a third time to clear the indeterminacy. Now plug in x equals 0. We get negative 1 over 6. Method 2, Taylor series visual cue. Sign x equals x minus x cubed over 6 plus x to the 5th over 120 and higher powers. Subtract x to form sign x minus x. The x terms cancel, leaving negative x cubed over 6 plus higher order terms. Divide by x cubed. We get negative 1 over 6 plus a term of order x squared. As x approaches 0, that small term goes to 0. So the limit is negative 1 over 6, matching our first method. Both pathways agree. The answer is negative 1/6. L'Hospital's rule shows the mechanics, while the Taylor series gives a fast visual cue by exposing the leading term. We will evaluate a classic trigonometric limit using a fast visual cue. Evaluate the limit as x approaches 0 of open parenthesis 1 minus cosine x close parenthesis divided by x squared. Step 1. Use the half-angle identity. Cosine x equals 1 minus 2 sine squared of x over 2. Rearranging 1 minus cosine x equals 2 sine squared of x over 2. Step 2. Substitute this directly into the limit. Step 3. Factor out the constant 2 and think of sine squared as a square. Step 4. Match the famous limit sign, u over u, by letting u equal x over 2. Then sine of x over 2 divided by x equals 1/2 times sine u over u. Squaring gives 1/4 times sine u over u squared. Step 5. Use the standard limit. The limit as u approaches 0 of sine u over u equals 1. Therefore, our limit equals 2 times 1/4 times 1 squared, which simplifies to 1/2. Visual cue recap. 1 minus cosine x becomes 2 sine squared of x over 2. Then sine of x over 2 over x becomes 1/2 times sine u over u. The famous limit gives 1, and the constants multiply to 1/2. Limit at infinity. We will evaluate the limit using a fast, rationalizing trick with every step shown clearly. Here is the problem. Step 1. Write the limit cleanly. We will call it capital L. Step 2. Multiply by the conjugate to rationalize the numerator. We multiply and divide by square root of x squared plus 4x plus x. Step 3. Simplify the numerator exactly. The squared square root becomes x squared plus 4x, and the minus x squared cancels, leaving 4x. Step 4. Factor out x from the square root. We write square root of x squared plus 4x as absolute value of x times square root of 1 plus 4 over x. Since x goes to positive infinity, absolute x equals x. Therefore, the denominator becomes x times parentheses, square root of 1 plus 4 over x plus 1. The x cancels, giving 4 over square root of 1 plus 4 over x plus 1. Step 5. Take the limit. As x grows, 4 over x goes to 0. So the denominator becomes square root of 1 plus 0 plus 1, which is 2. The limit equals 2. Final answer, 2.
Thank you for watching. Tap like, share, and comment, and then follow and subscribe for more quick problem-solving tips. Let's make maths simple. One video at a time only on Myverse Maths.